So we continue our little exploration of search heuristics for mixed integer nonlinear optimization. And we saw in the last lecture that these play an important role throughout the branch and bound tree search. And so in this lecture, I'm going to talk about three particular search heuristics. So those are heuristics that find us an initial integer and nonlinear feasible point. The goal is we want to ideally find an integer feasible point that also satisfies the nonlinear constraints for our mixed integer nonlinear optimization problem that we're solving. And so there's a whole host of these heuristics, and I'm just going to talk about three of them. So the feasibility pump and all its relatives are sort of a very famous set of heuristics. They're also very popular heuristics. So I'll talk a little bit about that, and then I'll talk about something called the undercover heuristic, because it's got the coolest name, and it's also got a cool connection to nonlinear optimization. And Pietro, not in the next lecture, but the next but one lecture, will have something similar that he's talking about there, but maybe in a slightly better setting. And then I'll tell you something about diving heuristics, because they're the simplest heuristics. So I'll talk about the most important one, or what everybody is doing, the feasibility pump, the one that I think has the coolest name, and the one that is the easiest to explain. So that was my choice for these heuristics. So the feasibility pump is a search heuristic for mixed integer nonlinear optimization. In general, it's for convex mixed integer nonlinear optimization, but there have been extensions to non-convex problems as well. And the goal, the basic idea is to treat the nonlinear constraints that we have and the integrality constraints in two separate subproblems, and to somehow do projections between these two feasible sets. Originally, this was proposed, a method like this was proposed by Fischetti and others for mixed integer linear optimization. And that is actually a very efficient method. And it has some more desirable properties than the feasibility pump has for mixed integer nonlinear optimization. The main part is that the mixed integer linear optimization feasibility pump only solves linear optimization subproblems. So it's very efficient in that sense at what it does at every iteration. The mixed integer nonlinear version solves also integer optimization problems as subproblems, and so it's not as efficient. And I can draw you a very quick picture of what this method is based on. So imagine you have two convex constraints. So here is a G1 of x is less than or equal to 0. And you have a second constraint. Here we go. G2 of x less than or equal to 0. And there are classes of methods which basically work by alternating projections. So you pick a point, that's your starting point, x0, and you simply project it onto the first set. So that's a projection, and that gives you your point x1. And now you project this new point onto the second set. So sort of there, and that gives you x2. And so there's a method of alternating directions or alternating projections that's well studied and converges for convex problems of this type. And you can have more than one convex set there. And so the question then is, how do we generalize this to the mixed integer nonlinear world? Well, we know how to project onto nonlinear constraints. What we don't know is how to project onto mixed integer linear feasible sets. And the method can be made to be finitely convergent, very much like outer approximation. So it's got a similar flavor to outer approximation and outer approximation cuts play an important role. So you recognize a lot of the machinery because you've seen this already. There are two subproblems involved here that I need to solve. The first one, I call it MINLO 1, or mixed integer linear optimization with a 1 norm. And I'm basically setting up a mixed integer linear optimization problem where I have a number of outer approximation cuts just for the constraints. So I'm not interested in this part in the objective. I want to find a feasible point. So I want to find a point that satisfies my nonlinear constraints and also integrality. And so I can compute the solution of this projection operator. This is an L1 norm projection. Normally in projections, the ones that I used here, that's the 2 norm projection, the orthogonal projection that we are used to, but projections can be defined in any norm. And so this is just a 1 norm projection there. And then I also construct a continuous set of iterates, which are the projection of this integer feasible point. So I find an integer feasible point here onto my nonlinear feasible set. So this is the standard 2 norm projection. There shouldn't be a square there. That's actually a mistake. So I have these 2 alternating projections using 2 separate norms. So just as a lead-in, why am I not using the 2 norm here? Does anybody have any ideas why I'm not using the 2 norm?
You want to solve a linear problem.
I want to solve a linear problem. If I use the 2 norm here, it would be a nonlinear problem because I would have a square root here. The 1 norm I can always rewrite as a linear set of constraints. And so that's why I want the 1 norm here. Okay, and so here's what the algorithm does. It alternates between these 2 projections, very much like an alternating projection method in the nonlinear smooth case. So we initialize the mix, we solve the continuous relaxation of the mixed integer nonlinear optimization problem, and we get x prime and y prime here. And then we initialize our L1 norm projection mixed integer linear optimization problem by linearizing around this first point. And I then obtain an integer feasible point by projecting onto this relaxation, onto this mixed integer linear optimization problem. So that gives me an integer feasible point. And then I'm going to see if I can project this point onto the nonlinear feasible set. So that gives me 2 points, y prime and x prime. And then now I have a new set of points and I add those to my outer approximation. So there's one important difference here to outer approximation. And in outer approximation, we used to fix the binary variables in this projection problem, but here we don't. They're actually free. So the binary variables are free in this projection problem, and we're just trying to find the closest point that sort of minimizes the projection of this integer point onto the nonlinear feasible set. And notice that if the point y dagger here were integer feasible, so if there were indeed a point such that this is integer feasible, then the solution would be y diamond and whatever point comes out that makes this constraint feasible in X, because that's the minimum that you can have in the norm here. Any other point would give you a value that's greater than 0. If you put y dagger in there, it's 0. And it's a convex problem, so we will find the global minimum. So if we have a feasible point, we will find it in this second step here, and we could actually stop there, right? This is where if we find a feasible point, we can stop. If we don't find a feasible point, then we add a linearization, a cut to our auto approximation. And so you have these 2 sequences, these points which are nonlinear feasible, the x prime, y prime, and the points that are polyhedral feasible. And the goal is that these 2 points somehow converge to each other. So you have some kind of zigzag that goes down. That's the picture that I have in mind when I think of this method. So this method is an alternating projection method. It projects nonlinear feasible point onto my outer approximations. So if I have a convex problem, then my linearizations are outer approximations, and I project onto the outer approximation. And the other problem projects the integer feasible point onto the nonlinear constraints that I have. And I terminate as soon as I find an integer feasible point. And we're using the L1 norm because it's affine, it's linear, and because I can equivalently write my 1 norm, which is just the sum of the absolute value difference between the solution that I'm looking for and my y prime, equivalently by introducing slack variables. So if I introduce slack variables Si here, then I can write the absolute values, each of these absolute values, with 2 inequalities. And you've probably seen this before. Either this side is non-negative, in which case Si will be equal to this value, or the other side is non-negative, in which case Si will be equal to that. And they're just the negative of one another. There's other ways of doing this, but this is maybe the best way, or it's one way of writing this as a set of inequality constraints. Cool. There's a nice lemma that there's some nice properties that these methods have. So if I look at these 2 sequences, the first sequence is the sequence of solutions to a mixed integer linear master problem with the L1 norm, where I'm minimizing, where I'm projecting using the L1 norm onto the linear feasible set. And the second set of problems are the projections onto the nonlinear feasible set. So I generate these 2 sequences of points that are feasible, integer polyhedral feasible, and points that are nonlinear feasible. And then if you make the assumption that you're using the same norms in both projections, which we're not doing, we're using the 1 norm and the 2 norm, but if we somehow use the same norms, then you can show this little lemma here. And this lemma just follows from the fact that the projections are optimal. So you just look at the objective function values and you see that these results hold. So that's sort of easy to see. So that just follows from the optimality of the projections, which is a nice little result. Notice that it's just inequalities, so it could be equal. So potentially they could stagnate. But there's a theorem that says they don't stagnate. And that relies on a lemma that we'd seen earlier. So you've seen this exact slide before. This is the outer approximation feasibility lemma, which was, I think, in lecture 23. So in an outer approximation, if the nonlinear optimization problem is infeasible, then the nonlinear optimization solvers will return us a solution to an infeasibility problem, which provides a certificate for convex problems that this nonlinear optimization problem is indeed infeasible. And then there is this nice lemma that says, if I now linearize my nonlinear functions around the point that comes out of this feasibility problem, then if I plug the original value y hat back in here, then this will be infeasible. And we showed that result here in class. And it just follows from the first order conditions of this nonlinear feasibility problem. And there's a similar result now for the feasibility pump. So in the feasibility pump, you solve a slightly different problem. You solve this projection problem. But if you linearize around the optimal solution of the projection problem, you can again show that you can not go back to the integer point that you plugged into the projection problem. And so the algorithm is actually finite, which is really nice. You could also add objective cuts if you wanted to. So you could go back to my mixed integer linear optimization problem. You could add your objective cuts, and each time you add an objective cut, you also have some upper bound possibly on the objective. You certainly have lower bounds, so you could add that as well if you wanted to. You don't have to. And then there is this nice paper by Claudia D'Ambrosio and co-workers on a storm of feasibility pumps. So you can do many more things with these feasibility pumps, and some of the results, the norm result, for example, is lifted from this paper. So there's lots of heuristics, and there's an increasing literature on feasibility pumps. So you can also come up with your own feasibility pump. So I want to go back here and just think about this a little bit, because you're doing your PhD students, so maybe some of you are interested in doing a new feasibility pump. So what are the expensive steps in this algorithm? We have 4 steps. And I give you a hint, setting L to L plus 1 is not the most expensive step. Oh, Ashutosh had guessed L equals L plus 1. Okay. Okay, so these two steps where you're solving optimization problems are the most expensive ones. So if you can come up with a way of not solving them or warm starting them or something, then you have a new version of a feasibility pump that might be faster and just as effective. And so the projection, maybe you solve this approximately. I don't know. But certainly the relaxation of a mixed integer linear optimization problem, maybe you can do this with some branch and cut instead or something. So there's ways there of improving it, of reworking these algorithms. But here's a second heuristic, which is the one that has the coolest name. It sort of alludes, Timo Berthold and Ambros Gleixner, they're from the Zusezentrum in Berlin. And Berlin is, of course, the spy capital of the world, or was the spy capital of the world in Germany. And so there's lots of undercover agents, and they thought they'll have an undercover heuristic. So the idea here is that you try again to apply mixed integer linear optimization techniques because they're the best developed techniques that are around. And what they want to do is they want to linearize non-convex functions by fixing variables. So that's actually that's a sort of interesting concept, right? You can take a nonlinear function, g of x1, x2, x3, and I just make something up, x1 squared times x2 plus x3. So in this function, which variable should I fix to make it a linear function? x1, I hope, right? If I fix x1, then I have a function that's just an affine function. And so the goal is then, but we want to fix as few variables as possible, because each time we fix a variable, we incur a cost. We make the objective potentially worse because we're no longer optimizing over this variable. And so what they do is they look at the sparsity, the non-zero pattern of the Hessian of the Lagrangian. So the Lagrangian function for our mixed integer nonlinear optimization problem is just the linear combination of the objective and the constraints weighted with these Lagrange multipliers lambda, which are non-negative. And this Lagrangian function now collects all the nonlinear terms that are in this optimization problem, so both the objective and the constraints. And the Hessian tells us something about how many of these terms are nonlinear, right? The Hessian term, the second derivative with respect to linear terms vanishes, and the second derivative with respect to quadratics is constant. The second derivative of this term here would be non-zero. So I can look at the Hessian of this term, see if I can not make a mistake. I should probably write down the gradient first. So that's 2x1, x2, x1 squared, and x3. And then I can write down the Hessian here. So I get it 2 x2. If I differentiate 2 x1 and a 0. This is a 0. Oh, 2 x1. Sorry, go on. x3 is, I made a mistake here. I made a mistake in the gradient. Yes, this is 1, and then this is 0, and then 2x1, this is 0. And then the Hessian, the rest is just zeros. Okay, good. So I can look at the non-zeros here, and that tells me what are the nonlinear interactions that are happening. And so all the nonlinear interactions correspond to this term here. So that potentially tells me which variables I should fix. So I form the Hessian of the Lagrangian, rewriting the Hessian of the Lagrangian, and then they define a graph where each vertex corresponds to one of the variables. So a vertex corresponds to one of the variables, rows or columns of my Hessian matrix, and there's an edge in the graph if and only if there's a non-zero entry. So there's an edge now between these, because I have non-zero entries here, there's an edge between these two vertices, and there's an edge that is to itself for this other vertex there. And the idea then is a minimum vertex cover gives the sort of least number of variables that I need to fix in order to get a mixed integer linear optimization problem. And so I have a little example that shows this, a slightly different example. So here there's one objective and one nonlinear constraint, 5 variables, and if you write down the Hessian graph, then this is the graph of the Hessian. So let's just look at this real quick. X2 that isn't connected nonlinearly to anything. So X2 is just isolated. There's no edge. There's an X1 cubed, so that's got an edge to itself. X3 and X4 are nonlinearly connected. They have an edge, and 4 and 5 have an edge. They're connected as well. Right, that's what they're doing. Sorry, that's so we can linearize it by fixing X1, X3, and X5. But in the second bullet is exactly what you're saying. You solve the minimum vertex cover problem. You're perfectly right that what we want to fix is X1 and X4. So we need to fix X1, and then if I fix X4, then all the vertices are sort of disconnected. And so fixing 2 variables here, X1 and X4, gives me a nonlinear optimization problem that I can then solve, or sorry, linear problem that I can then solve. Now there's a little bit more that goes into it. If I fix X4 at 0, then I'm in trouble, right? Because if I fix X4 to be 0, then 0 times 5 is certainly never going to be greater or equal to 1. So I need to be a little bit careful on how I do these fixings and maybe know more about the functions that are involved and the bounds that I want on the variables in order to fix it. No, that's an easy problem to solve. So finding the minimum vertex cover is an easy problem to solve. In graph theory, that's a well-known problem. So I can do this for very large graphs. That's the point, I think. They can do it for very large systems. Yeah, we want to find a good vertex cover and fix as few variables as possible. But there's probably something to look at also in terms of how you fix the variables, which I'm not doing here. Okay, so if you find a minimum or near optimum vertex cover, then the idea is to basically fix the variables that are in this minimum vertex cover. And most of the times those variables are likely to be continuous variables. It's because linear variables often only appear linearly in the problem, they're not going to be part of your vertex cover because they're already, linear variables don't have to be in the vertex cover. Here there was one linear variable x2, and you don't need to put this into your vertex cover. So most likely those are just continuous variables that you're fixing. And then you fix your continuous variables at some value, and it's still to be determined what is a good value for fixing these. And now the following problem then becomes a linear problem because we constructed the points in or we constructed the vertex cover so that when we fix these variables, the remainder of the problem is linear. So we now solve a mixed integer linear optimization problem. But because we fixed some of the variables, this just gives us an upper bound on the optimal solution. But this is relatively quick. You have to be kind of careful that if your function is like this power grid function here, then if fixing x1 and x2 still leaves me a nonlinearity. So I need to know a little bit more than just the Hessian information when I make the fixing. So in particular, in this case, fixing x1 and x2 does not give me a linear problem. It gives me a nonlinear problem. And those were one of the power grid functions that I just lifted from there. But this is really fixed by, instead of looking at the Hessian, what you should be looking at is probably the computational graph and analyzing the computational graph. And that gives you more information about the functions, the type of functions that you can fix. Just a question for you, can you extend this? So sometimes we have problems that are composed of smaller parts and subparts and components. And there's this notion of separability, which we saw yesterday, and partial separability, where you can sort of partially separate the Hessians. We had a little example in the tutorial yesterday. And there's an extension of that, which is also an extension or generalization of sparsity called group partial separability. So here, you could think about analyzing functions that have a particular structure, and then thinking about how would you apply these techniques in this setting. So again, this is just sort of food for thought a little bit. Okay, so I only talked about two. I'll talk about the diving heuristics in the next lecture. So I talked about the feasibility pump, which is probably the most popular of heuristics for solving mixed integer nonlinear optimization problems. There's a lot of variations of this method. It alternates between a nonlinear optimization problem that solves a projection onto the nonlinear feasible set and a mixed integer linear problem that collects outer approximations and corresponds to a projection onto the integer and the linearized or polyhedral feasible set. And so this method is, you can interpret that as also as an alternating projection method. And then I talked about undercover heuristics, but in this case, you have to watch out a little bit for nonlinearities. And so in addition to the Hessian, you need to look at the computational graph in some cases as well. But it's okay as long as you're using, for example, monomials and other functions, you have enough information there. Okay, so that's all I wanted to say about search heuristics. In the next slides, I'm going to talk about improvement heuristics, and some of these improvement heuristics are diving heuristics. I'll talk about that a little bit next. But let me know if there's questions, please, or if you have comments. Yes?
Among the two, which one is more?
I think it's the feasibility pump. I have not implemented them, so I'm really just guessing, but the feasibility pump solves a sequence of nonlinear and mixed integer linear optimization problems. Undercover solves potentially only one mixed integer linear optimization problem. But on the other hand, if you don't find a feasible point, then you may need to go back and unfix some of the variables. And I don't know if they've looked at this or how to do that. Sorry?
I'm assuming that on the contrary, feasibility pump is better for it.
Potentially, maybe, but the feasibility pump doesn't necessarily give you better solutions just because you're doing more work. The undercover heuristic works maybe better in non-convex settings, or where you have nonlinearities, where the feasibility pump, once you add too many linearizations, they become inconsistent, and so you have to be a little bit careful there. I think they're just alternatives. I actually like the undercover heuristic better because it's potentially has it's closer connection to nonlinear optimization, and if you implement it with the computational graph, I think it has more promise than the feasibility pump. Yes, I think for quadratics, undercover will work very well, and I think that's where they first thought about doing this for quadratic functions, especially for problems where it is just the objective that's a quadratic. So if only your objective is a quadratic, then you know that no matter what you fix, your point is feasible. And so in that case, it's a very powerful heuristic because you're fixing a subset of the variables to make the quadratic, to linearize the quadratic, and then solve that remaining linear optimization subproblem. So for quadratics, I think it works very well. And maybe there's a similar thing that works then for quadratic constraints. I don't know. I haven't enough experience with these things.